Hi guys, it's Daniel here, and today we're going to solve a classic number theory problem. So let's take a look. Show that for any n and any a, n factorial divides the product from k equals 0 to n minus 1 of a to the power of n minus a to the power of k. So let's see what we can do here. First of all, let's try to simplify this expression. By factoring out an a to the power of k, we can factor out first a to the power of 0, then an a to the power of 1, then an a to the power of 2, all the way to a to the power of n minus 1. So the total amount of a's to the power of some things that we factor out is, in fact, n minus 1 times n over 2, which is just n squared minus n over 2. And what remains is the product from k equals 0 to n minus 1, k equals 0 to n minus 1, of a to the n minus k minus 1. Now, in fact, this product is actually just equal to the product from k equals 1 to n of a to the power of k. And you can check for yourself that this is in fact correct. But I'll just skip this step for now. It's just equal to the product from k equals 1 to n of a to the power of k minus 1. So now I have that this original product expression is equal to this new product expression. And now we want to prove that n factorial divides this. So how do we do that? Well, one good strategy in number theory is to consider the primes. If we consider that for a prime p, if that prime p divides into n factorial, I don't know, some number of times, and it divides into this expression an equal or more number of times, and if this is true for all primes p, then that means n factorial must divide this expression. So in order to work with things like this, let's define some new notation. vee-pee of x. So this notation just equals the number of times that p divides into x. So for example, v2 of 12, well, 2 divides into 12 two times, because 4 is a factor of 12 and 8 is not a factor of 12, so v2 of 12 is just equal to 2. So what we're essentially trying to prove here is that for all primes p, we have to prove that vee-pee of n factorial is less than or equal to vee-pee of a to the n squared minus n over 2 times this product thing. I'll just call it x, since I'm lazy and I don't want to write the entire thing all over again. So we want to prove that this is true. And let's look at this thing. By a property of vee-pee, which is, well, if p divides into this expression some number of times, and p divides into this expression some number of times, then p must divide the entire expression, the sum of these two. And this is pretty obvious if you just think about it. So this is just equal to vee-pee of a to the n squared minus n over 2 plus vee-pee of x. And now we simplified the right hand side a little, so let's simplify the left hand side. This can be simplified by something called Legendre's formula. I'm not sure if I pronounced that right, but Legendre formula, Legendre's formula. And Legendre's formula states that this thing is simply equal to the sum from I equals 1 to infinity of the floor of n over p to the power of I. And I'll prove this in another video. But for now, just assume that this is correct. So now I have this other formula to calculate the value of vp of n factorial. Now it's time to prove our expression, less than or equal to this thing. Now we have two cases. The first case is very easy. If p divides a, then that means this expression is just equal to n squared minus n over 2. Right? And this is clearly greater than or equal to this expression, because we have that if we get rid of the floors, then it becomes something greater, right? So if we get rid of the floors, it becomes this thing is less than or equal to sum from I equals 1 to infinity of the floor, or not the floor, we got rid of those, n over p to the power of I, which is equal to by the geometric series summation formula, n over p minus 1. And this is clearly less than or equal to n squared minus n over 2. So therefore, if p, let's draw over here, p divides a is obvious. Now the second case is that p does not divide a. So let me write it over here. P does not divide a. And in this case, this entire expression, here, I'll write it in a different color. That will make things a little more clear. P does not divide a. If p does not divide a, then this entire thing becomes 0, because a to the power of anything, well, a doesn't have a factor of p, so a to the power of anything also doesn't have a factor of p, so this is just 0. So now what remains is we need to prove that vp of n factorial, which we established by Legendre's formula, is just I equals 1 sum from I equals 1 to infinity of the floor of n over p to the power of I. This is less than or equal to vp of x. And recall that x is the product of this stuff over here. So how do we do this? Well, recall Fermat's little theorem, which stated that a to the power of p minus 1 is congruent to 1 mod p. In other words, a to the power of p minus 1 is divisible by p. 0 mod p. So we can use this fact in this product right here. We notice that right here we have an a to the power of k minus 1. When k is a multiple of p minus 1, then this a to the power of k minus 1 has a factor of p. So how many k are there such that k is a multiple of p minus 1? Well, there's simply n over p minus 1 and take the floor of that. So there are this many terms where k is multiple of p minus 1. So what does this tell us? This tells us that vp of x is greater than or equal to n over p minus 1 floored. Why do we like this? Well, we like this because, oh look, we have this exact same expression as vp of n factorial. But there's a slight glitch that we haven't worked out yet. We found that vp of n factorial is less than or equal to n over p minus 1. And we also found that this entire expression is greater than or equal to the floor of n over p minus 1. But unfortunately we don't have that n over p minus 1 is less than or equal to the floor of n over p minus 1. In fact, the opposite is correct. So how do we work this out? Well, we notice that this entire expression right here, this thing, is an integer, because we're taking the floor of all these things. So if this integer is less than this real number, then it follows that this integer is actually less than or equal to the floor of this real number. Because if it's less than if it's an integer that's less than a real number, it must also be less than the floor of that real number. So now we're done, because we see that vp of n factorial is less than or equal to the floor of n over p minus 1, which is less than or equal to vp of x, which we found right here. So therefore, we see that this original expression right here is correct. So that means, since this argument works for all primes p, that n factorial must divide this entire expression. So that means n factorial divides product from k equals 0 to n minus 1 of a to the power of n minus a to the power of k, and we're done.
Hey guys, I'm here back with another math video. Today we're going to be proving the Cauchy-Schwarz inequality, and if you don't know what it is, it's right here. If you write it out algebraically, because I know this notation can be confusing, this is what it looks like.